Good morning, dear students. My name is Ferhan Mazher, and today is 4th April 2021, and we are studying the subject of physics. This is O Levels Physics 5054, and today we have set our hearts to solve May June 2010 2-1 paper. It's a theory paper. We call it paper 2. It's from the zone 1, May June 2010. And in this session, we will be solving the section B of this paper. The section A of this paper I have solved in another video, and you can go on to my YouTube channel and you can watch in the playlist where I have the playlist is paper 2, zone 1, section A. So there you can find these videos on the section A. But in here today, we are doing the section B of this paper. So let's start this paper, and the first question is coming on your screen. That's May June 2010 question uh, 2-1 paper, section B, starting from question number 9. It says the figure 9.1 shows a laboratory thermometer. State the range of the thermometer. The range of the thermometer, you see the maximum reading is 110. The minimum reading on the thermometer is -10. And you know the range is equals to maximum value measurement minus the minimum. So it will be 110 minus 10. Let me show you my work. I've done this. So the range will be the range of the thermometer will be 110 minus 10. So it will be 110 plus 10, 120 is the answer. Let's check the marking scheme. And the marking scheme says 120 degrees centigrade. So 110 plus 10, and it will be 120. So hopefully you have understood one mark question. Very simple, easy to get. State one change in the design of the thermometer to increase its range. If you want to increase the range, so the length of the thermometer can be made larger, or you can make the bore of this capillary in which the mercury is traveling. You can make it, or you can make this the bore of this capillary larger. If you make the bore of the capillary larger, then the range of the thermometer will increase. I have written this answer. Let me show you my answer. And it says make the bore of the capillary larger. Make the bore of the capillary larger. Okay, so let's check the marking scheme. What the marking scheme says use a longer thermometer or wider bore or less mercury or smaller bulb, not change liquid. Don't say change the liquid. Okay, because we have to change design of the liquid, design of the thermometer you need to change. Okay, so next question is describe how the behavior of a more sensitive thermometer is different from a less sensitive thermometer. The thermometers which are more sensitive, they show a larger change in the length of the mercury for every degree rise in the temperature as compared to the less sensitive thermometer. So let me show you my answer. Let me show, this is showing on the screen, and let's see. There will be a larger change in the length of the mercury for 1 degree centigrade change in the temperature. For more sensitive thermometer, there will be a larger change in the length of the mercury for 1 degree centigrade change in the temperature as compared to a less sensitive thermometer. So let's check the marking scheme. What the marking scheme says a mere smaller change in temperature or smaller range for same distance or larger expansion. The last one I have answered. The larger expansion or for the same temperature rise. There will be a larger expansion for the same temperature rise. This is the answer which I wrote. So you can write other answers as well. Okay, so we are moving to the next part. He says state one change in the design of the thermometer to make it more sensitive. A very, very famous question. If you want the thermometer to be more sensitive, there are a few things which you can do. One is you can make the bore narrow, or you can decrease the diameter of the bore of this capillary, or you can use a larger amount of the, but here we have to change the design. So that is the one thing which you can do. Make the bore of the capillary smaller. Make the bore of the capillary small. Let me check the marking scheme. The marking scheme says a larger bulb or more liquid or narrow bore tube or use liquid that expands more. Okay. So narrower bore, I have written this answer. Narrower bore is a very famous question, and this many times have came in the paper one MCQ paper. This thing comes many times. This particular concept. Describe how a clinical thermometer differs from a laboratory thermometer. A diagram may be included in your answer. It's a 3-mark question. He wants you to describe how clinical thermometer differs from a laboratory thermometer. A diagram may be included in your answer. 3-mark question. You see the clinical thermometer. It one very famous difference between the laboratory thermometer and the clinical thermometer, that the clinical thermometer have a constriction in it. Plus, the clinical thermometer, its range is less uh, as compared to the you know laboratory thermometer. I have written this answer, so let's check my answer. Clinical thermometer has a, here you can see. Let me increase the size so you can understand this. So clinical thermometer, you can see here I have shown there is a bend in the clinical thermometer. Here this bend is called constriction. Clinical thermometer has a smaller range. The clinical thermometer's range is very small as compared to the laboratory thermometer. Clinical thermometer has a smaller range as compared to the laboratory thermometer. Clinical thermometer is more sensitive as compared to the laboratory thermometer. Clinical thermometer has constriction. Clinical thermometer is more responsive to temperature changes. So these are few, and the body of the clinical thermometer is kind of convex lens, and it magnifies the reading. So it's kind of magnifying glass over the body of the clinical thermometer. So the reading becomes larger, magnified. So you can read it easily. Okay, so let's check the marking scheme. What the marking scheme says that clinical thermometer, the constriction and in narrowing, except mercury thread breaks at constriction. On cooling, a thermometer is a maximum thermometer range different, more sensitive, divisions further apart. Triangular cross section act as lens. This is what I was talking about. Triangular cross section acts as a lens. Thinner bulb, quick, responsive to temperature changes. Any 3 lines. Any 3 lines you can write. So here is the marking scheme. You can write a different answer which I wrote, but try to write the best answers possible. Okay. So let's move to the next part. It says in the space below, draw a label diagram of a thermocouple thermometer. So here we have to draw a thermocouple thermometer. It's a 2-mark question. I've done this. Let me show you my work. And here we go. So on your screen, a thermocouple is showing. Thermocouple is made by 2 wires. Both the wires are made of different metals. For example, here the blue wire is made of iron and the upper red one is made of copper. And in that we also put a voltmeter. The both the ends of these wires, they are twisted with each other. And one of the, we call it junction, one of them is put in a cold junction and one is put in the hot junction. So this is a label diagram of the thermocouple 2-mark question. Very easy. You can get full marks in it. And it's also very famous. Let me check the marking scheme. Different, the marking scheme says 2 different metals joined, connected to a meter, ammeter, galvanometer, voltmeter. So it's a 2-mark question. Very simple. Hopefully you will be able to get full marks from it. State 2 reasons why a thermocouple thermometer is sometimes a better choice than a laboratory thermometer. The thermocouple thermometer, it has some good things in it. Thermocouple thermometer, its range is very large. It can measure very low temperatures. It can can measure very high temperatures, so its range is quite large. Thermocouple thermometer, it can measure very quickly changing temperatures. Another very good thing about the thermocouple thermometer is that it can be connected with a data logger, and that can be connected to a computer. And on the computer, if you have the proper software, you connect the thermocouple with the data logger and into the computer. So what will happen with the time as the temperature will change, the data logger will make automatically the graph of the cooling or heating. So and so if the temperature will be changing very quickly by this method, you will be able to note it down. So I written my answers. Let me show you my answers. It says that let me increase the size. So thermocouple has larger range than the laboratory thermometer. Thermocouple can measure quickly changing temperature. You just have to mention two good things about the thermocouple. So there are so many good things about the thermocouple. Low, high temperature or greater range, responds quickly, measure rapidly changing temperatures, measure temperature at a point, electronic output more robust. It's more robust. You can take it anywhere. Measures temperature at a distance. You can, with the help of the thermocouple, because these are wires, you can make them long, and they act like a probe. You can make like them 6 feet long, and then you can use it to measure the temperature of a very hot body, and you don't have to go near to that body by at a distance of 6 to 7 feet. You can measure the temperature of that body. For example, in your textbook, there is a diagram in which a scientist is standing near lava, and he's measuring its temperature, and he has a thermocouple and he has a probe. So you can make those wires long, and that's like a probe. And by standing like 6 feet away, you can measure the temperature. The hot junction will be that lava. You can put that in the lava, and you can measure the temperature. So the measure temperatures at a distance mean this thing. This diagram is also in your textbook. So I hope you will be able to write to able to get these 2 marks. Okay, so next E part is figure 9.2, shows a copper block of mass 1.8 kg with 2 holes in the top. An 80-watt heater is placed in one hole and a thermometer in the other. So we have a block of metal. We have drilled 2 holes in them, and in one hole we have put a heater, and in the other hole we have put a thermometer. The heater is switched on for 5 minutes. Assume that no energy is lost from the block. Calculate the energy supplied to the block. If you know the power of the heater and you know the time, you can just multiply them and you will know how much energy is being supplied. So I've done this on the paper. Let me show you my work. And here we go. So the energy is equals to power multiply time, 80 watt multiply. The time will not take in minutes here. So I will multiply it with 60 to convert it to seconds. So it will be 80 watt multiply 5 into 60, and the final answer will be 24,000 joules. So the energy given out by the heater in 5 minutes is 24,000 joules. So let's check the marking scheme. The marking scheme says 24,000 joules. You can see the marking scheme on your screen. 24,000 joules. 24,000 joules is showing. Okay, so move to the next part. And the next part says the specific heat capacity of the copper is 390 joules per kg per degree centigrade. Calculate the rise in the temperature of the block. So, the mass of the block is 1 point was given here. The mass of the block is 1.8 kg, and we know 24,000 joule energy is given. And he wants us to find out the rise in the temperature, and the specific heat capacity of the copper is also given. When there is a change in the temperature is involved, the formula for the heat is mc delta theta. Heat is equals to mc delta theta, where heat is the heat you supplied, M is the mass of the body, which is 1.8 kg. C is the specific heat capacity of this block, that's 390 joules per kg per degree centigrade. And delta theta means change in the temperature, and that is the question. So let me show you my work, and here we come. Let me increase the size. And so heat is equals to mc delta theta. Heat is 24,000. M is 1.8 kg. And the C value is 390. Delta theta is question. So I will make delta theta the subject of the formula. So on your calculator, write 24,000 divided by 1.8 divided by 390 equals to, so the change in the temperature will be 34.19. So there will be a change of temperature of 34 degrees. So let's check the marking scheme. The marking scheme says 34 degrees centigrade. So I hope that you have, it's a 2 marks numerical, and I hope you have understood a very, very famous concept. When the temperature changes, we use this equation, and heat is equal to mc delta theta. So let's move to the next part, and the next part is the next question. This is actually question number 10. Figure 10.1 shows a car braking system. The brake fluid is an oily liquid. So here you have a brake paddle. So when you press the brake paddle, so here we have the pivot. Here we have the master piston. So when you will press the brake paddle, this master piston will move to the left side, to the right side, sorry, and it will press this. It will push this oil, so it will apply force on the oil, and the oil will, oil is incompressible. So according to the Pascal's principle, whatever will be the pressure created in this master piston, in this master cylinder by the master piston, the same pressure will be transmitted here into the slave piston. So the oil here, it will, the pressure, whatever the pressure is here, same pressure will be transmitted here to the oil. This is called the Pascal's principle. So what will happen? This oil, the pressure here, that will exert force on these brake shoes, and the brake shoes, they will rub against the brake drums, and this is how the brakes will work. The brake drum rotates with the wheel of the car. So the brake drum is basically attached with the wheel of the car. So explain how pushing the brake pedal makes the brake shoes rub against the drum. This is that explanation which I just gave you. So whatever is when the piston, when this brake pedal is pressed, this master pistons move towards right. The oil transmits the pressure, whatever the pressure is created here, same pressure is created in the slave pistons, and the slave pistons apply force on the brake shoes, and they rub against the brake drums, and this is how the brakes are applied. So let me read my answer, and I've written this answer. Master piston creates pressure in brake fluid. Same pressure is transmitted to the slave piston. That's the Pascal's principle. Slave piston, due to this pressure, exerts force on the brake shoes, and the brake shoes then rub against the brake drums. So let's check the marking scheme. What the marking scheme says about this. Okay, so what will happen? The master cylinder creates pressure in the brake fluid, or the pressure from master piston is transmitted to the slave piston. 1 mark for this. And the fluid pressure produces force or push, don't say press, on the slave piston, or force from the master piston transmitted to the slave piston. So I think there is again some issue with the internet today. The internet is not that good, and the screen which I have shared, it has stopped working. So let me stop the sharing and then again share it. So today the internet is showing some strange problems. So the screen which I shared from my desktop, something happened with this. So we were on this part. So the master piston creates pressure in the brake fluid. Some pressure is transmitted to the slave piston. Slave piston, due to this pressure, exerts force on the brake shoes. So let's check the marking scheme. And the marking scheme says the master cylinder creates pressure in the brake fluid or pressure from the master piston transmitted to the slave piston. One mark is, of course, saying this. And the fluid or pressure produces force or push. And he says not press on slave piston or force from the master piston transmitted to the slave piston. So it's a two-mark question, and due to the internet, there was some interruption in the sharing of the screen. The screen was stuck. I don't know. Okay. So the question is, the next part is the cross-sectional area of the master piston is 2 centimeters square. A force of 140 Newton is applied to the master piston. Calculate the pressure exerted in the brake fluid by the master piston. So I know the area of the master piston. We know the force applied on the master piston. So we can calculate the pressure. Pressure is force divided by area. So, and the answer we want is Newton per centimeter square. So let me show you my work. So very easy. It's very easy. Let me show you this. Okay. So the pressure is equals to force divided by area. So 140 Newton force is applied, and the pressure and the area is 2 centimeters square. So 140 divided by 2, it will be 70 Newton per centimeter square. So let's check the marking scheme. And the marking scheme says 70 140 divided by 2 and 70 Newton per centimeter square is the answer. B first part, and I hope that you have understood this. Okay, the next part is the cross-sectional area of each slave piston is 2.8 centimeters square. Calculate the force exerted on each slave piston by the brake fluid. So see, whatever is the pressure which is created in the master cylinder, same pressure through the braking fluid is transmitted into the slave cylinder. So I know the pressure already there, and that will be 70 Newton per centimeter square. And I know the area of that slave piston. So I can calculate the force. So force will be pressure multiply area. Let me show you my work. So the force will be equal, the pressure is equals to F by A. So F pressure is 70 Newton, same Newton per centimeter square. The area there is 2.8 centimeters square. So F will be 70 multiplied 2.8, and the answer will be 196 Newton, approximately 200 Newton. So because in the marking scheme he says 200 Newton, we have according to the same, whatever the data, your data has two significant figures. That's why the answer is also 200 Newtons. We have the actual answer is 196 Newton, but we have converted into two significant figures because the data has only two significant figures in it. So 200 Newton is the answer, or 196 is also acceptable. Don't worry. The next question is the force exerted on the master piston is greater than the force applied by the foot on the brake pedal using the principle of moments. Explain this. You see, he's talking about this portion here. You see the brake pedal, you press, you applied the force here, and the master piston applied the force here. So he says the force here in the master piston is larger than the force you applied on the brake pedal. The reason is very simple. You see, if you look at this body carefully, here is the pivot. So whatever will be the moment produced here, if you produce an anti-clockwise moment, same anti-clockwise moment will be produced in the master piston. This force which you applied by your feet, that its moment arm is quite large, and the moment arm of the master piston is smaller. It's perpendicular distance from the pivot. That's the moment arm. You see, the moment produced here and the moment produced in the master piston, they both are equal to each other. But because the moment arm of the master piston is smaller, that's why the force produced here should be larger. Because the moment is the product of force and the moment arm. So if the moment arm is smaller and the moment needs to be the same as produced by the brake pedal, then the force has to be greater, has to be larger. So this is question number B, third part. It's the 2-mark question. I've written this answer also. Let me show you my answer. So hopefully this is visible to you. Let me increase the size. Let me increase the size so I it's become readable. Okay. So now moment produced by force on brake pedal and moment produced by force on master piston are equal. Moment arm of the master piston is smaller as compared to the moment arm of the brake pedal. So the force on the master piston has to be larger to have the same moment as that of the brake pedal, because the moment on both the places was equal. So the master piston has smaller moment arm. So the force produced there has to be larger. It's a very little difficult answer to write and to comprehend. Okay, so let's check the marking scheme. What the marking scheme says. The marking scheme says distance. Here, third part answer is on your screen. And the screen is not sharing again. So let's stop first of all the sharing. Something is wrong. So first of all, I have to stop sharing and then again I share. So you see, there is some issue with the sharing of the, I don't know whether my sound is being properly recorded or not, but let's see after the recording what happens. So we are done with this 2 mark question. Hopefully I have shown you the marking scheme. The distance foot to pivot larger than the piston to pivot. There's 1 mark for this. And force into distance is constant. So they have the same moment on both the sides. So because the product of force and distance, moment arm has to be the same. So if the moment arm is smaller, then the force has to be the larger to get the same moment. So let's move to the next part. It says figure 10.2 shows a master cylinder sealed at one end instead of brake fluid. The cylinder contains air. So here I don't have the oil. Here we have air. So the area of the piston is 2 centimeters square. From here it is sealed. Inside here I have gas. When a force is applied to the piston, the length d changes from 6 centimeter to 4 centimeter. The pressure of the air increases, but the temperature stays constant. Describe how the molecules of the air exert the pressure. It's a very simple 1 mark question. You see the molecules of the air, they are traveling and they are moving randomly. They are moving in all directions randomly. So what happened there during their motion? They come across, they collide with the walls of the container, and they also collide with the piston. So when they collide with the walls of the container or with the piston, they exert force on that wall, and that force per unit area will be pressure. I've written this answer. Let me show you my answer. So here we go. Let me reduce the size. So here we go. Air molecules are moving randomly. They collide with walls of container and piston. They exert force on collision with the walls. Force per unit area is pressure. So hopefully you have understood. And let's check the marking scheme. What the marking scheme says, it's a 2 mark question. Molecules hit, sorry, it's a 1 mark question. Molecules hit against the walls, piston, ignore, hit each other. So what the answer I wrote, that's good answer. So next question, explain why the pressure increases even though the temperature stays constant. You see, when the piston is moving in, the piston, the piston here that's moving in, it's moving to the right. So the volume of the gas will become small. You see, if the temperature is constant, the volume of the gas is decreasing. When the volume of the gas decreases, so the pressure increases. Gas pressure and the volume of the gas, if the temperature is constant, they are inversely proportional to each other. So the volume of the gas will decrease, the pressure of the gas will, sorry, the volume of the gas will decrease, the pressure of the gas will increase. He says, explain why the pressure increases even though the temperature stays constant. There are two things. When the volume of the gas decreases, you see the volume, the number of molecules per unit volume increases. The collision frequency of the air molecules with the walls of the container, that increases. So more number of molecules hit per unit area. So that's why the pressure will increase. I've written this answer. Let me show you. Okay. So our answer will be molecules per unit volume increased, collision frequency increased of air molecules with the walls of container. Molecules have to travel less distance to collide with the wall. These are some reasons. Let me show you the marking scheme. The marking scheme says, oh, the marking scheme says hit, this is a two mark question, hit more often, more frequently, and small volume or molecules closer, less space to travel. They have to travel less space before clear. So next part is, he says that the initial pressure of the air inside the cylinder is 1 expo 5 Pascal. Calculate the final pressure of the air. State the formula that you use in your calculation. According to, if the temperature is constant and the volume of the gas is changing, then the pressure will change. And we have the formula P1 V1 equals to P2 V2. P1 V1 equals to P2 V2. And let me show you my work, and then we see. So P1 V1 equals to P2 V2. P1, a volume can be written as cross-sectional area multiplied the length of that cylinder in which you have the gas. So cross-sectional area in at the P1 and the P2 side, both sides the cross-sectional area is same. So the length of L1 and L2, area and area will be cancelled from both sides. So you will have the formula P1 L1 equals to P2 L2. So P1 when exposed 5 Pascal and the length 1 is 6 centimeter, and P2 is the question, and L2 is 4 centimeter. So make the P2 alone, and this 4 will go on the other side and it will divide there. So on your calculator, in your calculator, write 6 expo 5 divided 4 equals to, and the answer will be 1.5 expo 5 Pascal. 1.5 expo 5 Pascal. Let me check the marking scheme. The marking scheme says 1.5 expo 5 Pascal. So hopefully you have understood this numerical. So let's go to the next part, and the next part is air bubbles form in the brake fluid of the figure 10.1. State the effect this has on the braking system. So he says if he's talking about that, he's not talking about this thing now. He's talking about this. Okay, here I have oil. So in that oil we have now air bubbles. So in that braking fluid, if you have air bubbles, you see the air bubbles have air in those bubbles, and because the fluid, the oil, the brake oil is incompressible. But if it has air bubble, it's a big problem if it has air bubbles, because the air bubbles will have air, and that air is compressible. So when you will the master piston, it will move to the right. So because if the oil has air bubbles in it, and that those air bubbles, they will compress. So when they compress, the pressure cannot be the same pressure cannot be transmitted to the slave slave cylinder or slave piston. So if there are air bubbles present, then the same pressure cannot be transmitted to the other end in the hydraulic brakes. I've written this answer. Let me show you my answer. Air bubbles are compressible, so the same pressure will be not transmitted from master piston to the slave piston because air bubbles are compressible. So let's check the marking scheme. What the marking scheme says, the marking scheme says air bubble compresses, reduces in volume, or breaks pushed further. The brakes become spongy, ignores efficiency, less pressure, less force transmitted. So the pressure which is transmitted will be less. But as the Pascal principle says, the same pressure will be transmitted. But if the air bubbles are present, then the same pressure cannot be transmitted. So let's move to the next part. The next part is question number 11. It says, complete the table of the figure 11.1. Here are types of radiation: alpha particles, beta particles, gamma rays. Then the nature of the radiation. He says alpha particles have two protons and two neutrons, and charge is positive. So we have to complete this. So let me show you. I have done completed this table. So the beta particles, they are like one electron and they have negative charge. Gamma rays are electromagnetic waves and they are neutral. They don't have charge on. This is how you will complete that table. So let's check the marking scheme. What the marking scheme says. The marking scheme says that electrons, negative, electromagnetic high frequency wave, and they are neutral. So this is how you will complete that table. Okay, so next we have that table completion is of 4 marks. It's easy marks. The technetium 99 is a radioactive isotope that emits gamma rays and it has a half-life of 6 hours. In a hospital, a solution containing this isotope is injected into a patient. The solution travels around the body and the isotope attaches to cancer cells. A few hours after the injection, an instrument is used to detect the gamma rays emitted by the isotope. A high reading on the instrument indicates the position of the cancer cells. Explain what is meant by half-life. A very, very famous 2 mark question. What is meant by half-life? It's the average time duration in which half of a given sample of radioactive isotope will decay. So I've written this and this definition. Let me show you my definition. Uh, Here we go. Average uh, average time duration in which half of a radioactive sample will decay. Average time duration in which half of a radioactive sample will decay. So don't forget this definition. Let's check from the marking scheme. What the marking scheme says. Marking scheme says time taken to have activity or number of atoms, nuclei, or count rate, or ignore radioactivity, mass, volume, amount, number of particles, molecules, a nucleus to have. Okay, so it's the average time. The definition which I gave you, remember that definition is good. It will get you 2 marks. Explain why an isotope emitting gamma rays is used rather than an isotope emitting alpha particle. You see, here what is happening, you injected that solution into the body of the patient, and then that solution goes and attaches it's this that radioactive thing attaches itself to with the cancer cells. And you see, we use a detector from outside the body, and wherever those radiation is coming in large amounts, we know that there are the cancer cells. So the radiation has to come out of the body. The detector is outside the body. So the radiation should be able to penetrate through the organs, through the flesh, through the skin. And if you use an alpha particle, you see the alpha particles, their penetration power is very low. In air, they can only penetrate 3 to 5 centimeter. They cannot pass through the paper. So the alpha particles will not be, if you put the alpha particle source which is emitting alpha particles and you inject into the patient, the alpha particles, their penetration power is very low. So they will be not, the alpha particles will not be able to penetrate through the flesh and through the skin and through the organs. So an outside detector will not be able to detect the alpha particles. So we don't use alpha particles. We use gamma rays because the gamma rays penetration power is quite large. They can travel to many kilometers, and thousands of meters they can travel, penetrate in the air. So they can easily penetrate through the organs and the flesh, and they can come out of the body, and the detector outside the body will be able to detect them. So we do not use alpha particles because their penetration power is very low. I've written this answer. Let me show you my answer. And penetration power of the alpha particles is very low. They will be not able to penetrate through organs and flesh. So detector will not be able to detect their presence in the body. Gamma has higher penetration power, so they can be detected by a detector from outside the body. So it's a 2 mark question. I hope you have understood. And let's see what the marking scheme says. The marking scheme says that the alpha stopped by the body, flesh, skin, or cannot penetrate body, skin, or causes damage. Alpha particles ionization power is high, so they can also cause damage. Gamma penetrates body, not absorbed, or can be detected outside body or cause less or no damage to the body. Gamma rays, their ionizing power is less. That's why um, the ionization is the problem if you use alpha particles. The next question is explain why using an isotope with a half-life of 6 hours is better than using an isotope with a half-life of 6 minutes. You see, why not use the isotope whose half-life is just 6 minutes? You see, 6 hours is a good time. You see, you injected the solution into the body, and then that injection will travel in the body, and that will reach to the cancer cells, and then you will use the detector to find where are the cancer cells. So this, for this process, 6 hours is a good time. So enough time so that the solution can reach the cancer cells, and then doctors and nurses, they will have enough time to do their diagnose, uh, for doctor to diagnose and to perform his tests. Then you will have enough time. If the half life is just 6 minutes, then you will not have an ample time to do all this inquiry that where are the cancer cells. So I have written this answer. Let me show you my answer. And it says six hours. 6 hours will be enough time to reach the cancer cells, for the solution to reach the cancer cells. Enough time for doctors to do their investigations. Whatever investigation they want to do, they can do. Let's check the marking scheme. What the marking scheme says, takes time for isotope, because it takes time for the isotope to spread, investigation and experiments. So 5 minutes, if the time is 6 minutes, half life is 6 minutes, it will be too short for all these things. I hope you have understood. Then the question is, explain why using an isotope with a half life of 6 hours is better than using an isotope with a half life of 6 days. You see, we can use a radioactive source whose half life is just 6 days, but we don't use that. We use the isotope whose half life is six hours. Why? Because if you use isotope with the 6 days half life, then it will remain in the body of the patient for a very, very long time. The body, because the radioactive sample, the radioactive solution is inside the body of the patient, so the body will be radiated and it will remain radiated for very long time. So 6 days is a too much time. So the patient has to remain in the hospital for a very long time. 6 hours is the better time. Okay, let me read my answer. And here's to say, patient will be radiated for a very long time if half life is 6 days. it can be damaging. So that long exposure to the radiation, that can be damaging. Let's check the marking scheme. Radioactive for longer time. The person will remain radioactive for a longer time. That will be more dangerous, more damage, causes damage. So it's better to use a sample whose half life is just 6 hours. A different radioactive isotope used in hospitals has a half life of 13 hours. A sample of this isotope and a detector are placed in a lead box. The count rate is recorded every minute for 3 minutes. The values obtained are 3202, 3140, and 3258 counts per minute. Explain why the three readings are not the same. Because the radiation is a random process. That's why every time you take the reading, it is little different from each other. So the simple answer is that the radiation is a random process. Let me show you my answer here. Here you see. C first part, radioactive decay is a random process. That's why every time you take the reading of the sample, it's different. So let's check the marking scheme. What the marking scheme says radioactive emission is random. 1 mark. Then we have the next question, and it says estimate the time taken for the average count rate to fall to 200 counts per minute. So how much time it will take to fall to 200 counts per minute? It's a 3 mark question. So first of all, I will take the average of these three readings. That will give me the initial count rate. So I will add these three and I will divide it with three. I will get the average count rate. And the half life is 13 hours. Okay. So I've done this on a paper. Let me show you my work. Okay. So first of all, I will take the average count. That is, I will add the three readings given and I will divide them with three. So on your calculator, write these three values: 3202 plus 3140 plus 3258 equals to, and divide it with 3. So the final answer will be 3200. So the average count rate is 3200. Then at 0 hours, it is 3200. When one half life is passed, this reading will become half. When another half life has passed, this reading will further half. When another half life has passed, this reading will become half. And when another half life has passed, this will become further half. So from 3200 um, to become 200, the count rate will become 200. It will take 52 hours. Every half life is of 13 hours. So there are 4, 1, 2, 3, 4 half lives have passed. So 52 hours time has passed. So I hope you have understood this. So let's check the marking scheme. So marking scheme say 52 hours. So hopefully you have understood that how we came to know that how much total time has passed, and each half-life was of 13 hours. So then at the last we have the question. This was 3 mark question. Then the last part is the sample and the detector are taken out of the lead box. The count rate rises slightly because of the background radiation. State one cause of the background radiation. There are many causes of the background radiation. For example, the cosmic rays which are coming out from outer space, they cause the background radiation. There might be some ores under the soil, some rocks which are radioactive, and the background radiation can be due to that. And due to there might be some radioactive waste dumped in some area or away from that area, but its radiation is coming. So we have the many reasons for that background radiation. So famous, write the famous answer. I've written the famous answer here. You can see the cosmic rays from the outer space. The cosmic rays which are coming from the outer space, they call the background radiation. This is one reason. Let me check the marking scheme. Marking scheme says rocks, cosmic rays, radon gas, or nuclear fallout. So 1 mark question. So my dear students, and we have reached the end of this paper today. In this session, we have worked on physics 5054 to 1 section B. It's May June 2010. May June 2010 paper. We have solved paper 2, and we have in this session we have only attempted the section B of this paper, May June 2010 to 1. And the section A of this paper we have solved in another session, in another video. You can find them on my YouTube channel. So I hope that this video has been useful to you, and your the grades of your physics, the concepts of your physics, they will improve day by day. So hopefully this everything is helpful to you. So thank you very much everybody for today, and I hope that you are improving. And if these videos are helpful to you, kindly don't forget to subscribe to my channel. Also recommend these videos to your friends who are in O levels final year. So thank you very much everybody, and have a good day. God bless you all.